And we're live. So welcome back, everyone, to another session of a Mette with a fantastic researcher. Today we have the awesome researcher Ahmed, who's going to be talking to us about multitask reinforcement learning with mixture of orthogonal experts. One of his amazing work that has recently been accepted at iClear 2024. Ahmed, the floor is yours. We're very excited to have you with us. Please go ahead.
Thank you, Haitham, for the opportunity. So, as Haitham said, this is my recent accepted paper at ICLR 2024. It's co-supervised by Jan Peters and Carlo Deramo. From the topic, we are dealing with multitask reinforcement learning, where the objective and the main objective is to have a single agent that can learn multiple tasks, deals with different skills and different objects. But the question is, how can I design such an agent or such an algorithm that can make such an agent learn different tasks? Mathematically speaking, I will use in this presentation this formulation, which is called block contextual Markov decision process, which is similar to the Markov decision process, but for multitask reinforcement learning, where it consists of a tuple of C, which is like the context space, S, the state space, action space, and the difference is having an M, which is like a mapping function that maps the context that I will try to solve to some MDB components. And those components could be like the reward function, that probability transition matrix. And also for this specific formulation, we assume that each task accesses only a partial subset of the true state space. For example, like for MetaWord, all of these tasks is represented by a single vector, single d-dimensional vector. However, the components for this vector is the semantics of this vector is different. For example, one component in this vector can define object one, but object one can be a drawer, can be a door, can be a button, and whatever. The objective of multitask reinforcement learning is to maximize the average cumulative return. And in the recent years, the focus of the literature has been directed toward sharing knowledge, as we all know, but sharing compositional knowledge. For example, the recent work, CARE, tried to learn a mixture of state encoders that tries to map every state to a K representations. And then
Ahmed, sorry to interrupt. Could you go back, please, one slide?
Yeah, sure.
Can you explain M prime again? I don't think I understood M prime, actually.
M prime. So M prime is like a mapping function. So if you give if you give this like MDB formulation the context that you want to solve, for example, like as here in these examples, the context, for example, 0 represent the task of like clicking the button, then it will give you a set of parameters that will define your MDB that you will try to solve. For example, it will give you like the reward function for this environment. It will give you the dynamics of this environment represented by the probability transition matrix, and also it will give you a subset of the state space, and of course the initial distribution. I hope I was clear. So I mean, every time you encounter a task, because now for a normal MDB setting, you don't have a context at all. You don't have like a parameter that can differentiate between different tasks. So in this formulation, you have a context space, and from this context space, you sample, or you can like select different context. And by doing this mapping function using the function m prime, you can now map the context to some parameters that will define your MDB for each of the tasks. Can give you like a reward function, the dynamics, and so on.
Got it. Okay, and you're assuming that all the MDPs have the same state and action space.
It has the same action space, and it has the same true state space. What I mean by this true action space, it's unknown, by the way, to the agent. It doesn't know this true state space. It does know only the partial state space that interacts with every of the tasks. So every task, you have like a state space which is a subset of the original unknown true state space. Again, I can elaborate more.
Okay,
So
understood.
if you, yeah, okay. So for the related work, as I was saying, that the direction has been like directed toward learning a composition or sharing compositional knowledge. How can we do that? Maybe for example, in the representation space, we can learn a set of encoders, k encoders, and then using those k encoders, we can map the single state to k representations. And then, for example, here in care, they use an attention mechanism to combine those k representations given some metadata. So the metadata can be like a task description, can be like a one-hot vector or whatever. Another recent approach focus on the parametric level, where instead of learning like k experts, it learns compositional policy, and also uses some metadata, for example, like one-hot vector, to generate task-specific weights that will combine those set of parameters. And from this set of parameters that we can assume that they are also a mixture of policies, you can generate now task-specific policies. For example, one for the button press, for the door open, and so on, and so on, and so on. So all of the recent approaches have been focused on sharing compositional knowledge by training some kind of a mixture of experts. However, there is no guarantee of the diversity. I cannot guarantee the diversity of such experts. For example, one thing can happen is that all of the experts or few of them can collapse to a single model. Or maybe the representation generated, for example, from all of these experts can be like similar to each other. So they are not actually capturing the relevant components between shared that should be shared between all of the tasks. For example, the expert should like capture common objects in the environment, common skills that should be performed, or maybe like some physical quantities. So in this work, we focus on like sharing also compositional knowledge, but we want to share them in orthogonal way. So we want to share orthogonal representations so that we can ensure that all of the representations are different from each other. We propose a different definition of the Markov decision process. We call it Stifel contextual Markov decision process, which is still similar to the one we saw before. However, we added another function called phi. This function tries to map every state to a k orthonormal representations, Vs. And it happens to be that this Vs, it's actually a point on what is called Stifel manifold, which is like a smooth manifold. And the Stifel manifold is defined by the set of all orthonormal k vectors in the Euclidean space Rt. However, now since we introduced this function phi, how can I approximate this function? In this work, we approximated this function using also a mixture of experts, like a bunch of neural networks, and with some learnable parameters phi. And we form or formulate.
I'm sorry, Ahmed. Quick question. So Stifel manifold, am I right that it's basically a collection of all orthogonal matrices
Yes.
over some? Yeah. Okay.
In
Gotcha.
our case, it's k times d.
Okay. I see. Gotcha. Yeah.
So now this function, we approximate this function phi using a mixture of experts, and we also learn like some kind of a compositional policy that consists of two parts. The first part is the mixture of experts, but it's totally task agnostic. We just the rule of this phi function, or in our case now after the approximation, it's the h. So this h just maps every state to a k orthonormal representations, agnostically, without knowing the context that we are trying now to solve. Then we have like the task-specific output module or output layer that we will use to now generate the appropriate actions accordingly. And we will refine
Ahmed? So if I understood you correctly, the main idea of imposing this constraint is that now you can guarantee that each neural network is kind of orthogonal to another neural network, so it learns a specific skill that cannot be written as a linear combination of another skill learned by another network.
Yeah. Or I can exactly say that now I can express every state via different, totally different representations. I can assure you that those representations are not linearly dependent, are totally different, are not even close to each other in terms of similarity, semantics, and so on, by doing this orthogonal TS. And our objective that those experts, after doing this orthogonalization, it eventually will be totally different from each other in terms of like the roles of expert one, expert two, and so on. Every one of those experts will capture different properties in the environment, but
Okay.
without manually designing them, because this is
Mhm.
like a hassle.
Okay. By the way, there's a bit of noise coming from your earphone. I think we could hear
Really?
that. Yeah, maybe the microphone is moving around. Yeah. Okay.
Yeah. How about now?
Oh, it's perfect now. Yeah.
Okay. So now I was saying that we refine the objective function by changing the unconstrained objective function to a constrained objective function. Still, we are optimizing for the same objective, which is like the average cumulative return. But now we have a constraint, which which is the following: for every state, I want to ensure that the representation generated from the mixture of experts is orthonormal. But how to do that? This is our algorithm, mixture of orthogonal experts, Moore. So this is like an illustration of Moore. The first step, as we said, we generate some K representations using our mixture of experts. And then to satisfy such constraint that I showed you before, we use Gram-Schmidt. And we are using Gram-Schmidt to orthogonalize those representations to another orthogonalized version. And as we discussed before, this representations is like a matrix, K times D, and it belongs to the Stiefel manifold. But all of the two steps are totally agnostic, regardless the task that we are trying to solve, regardless the context. Now, now we need to add now the context part. So we treat those orthogonal representations as like some kind of a basis that span the space that represent the single state that we just encoded. And then I'm using those bases to interpolate some task-specific representations using some task-specific weights. For example, here I'm using also a task encoder as the previous works, and using this task encoder, given the context, I will generate some weights, and then I will use those weights to combine the bases to generate the task-specific representations. And finally, I use the output layer or the output network, it depends, to generate the action, the action that I will take now for this task. Since mainly I will deal with like actor-critic setting, the same framework that I just showed can be employed for the actor and for the critic. For the actor, it's similar to what I just described. However, for the critic, now I will encode, instead of just the state, I will encode the state and action. We have been we tested or evaluated our approach on MetaWord, which is like a really famous multitask reinforcement learning benchmark. So this benchmark consists of like different manipulation tasks. It has two scenarios: the MT10, 10 tasks, 50 MT50, 50 tasks. The state is represented by 39-dimensional vector, and the action space represented by the 3D change in the vector, and another component that represents the normalized torque applied to the gripper. For the baselines, we compared Moore against SAC, which is SAC represents the single task performance, which is like training SAC on all of the tasks and then average the performance. So there is no multitask happening. And then empty SAC, which is like the adaptation of SAC for multitask setting. And SAC plus film, just SAC using like a conditional policy with the film module. And BC grad is a really strong state related work for multitask reinforcement learning that tries to solve the task interference problem by doing some gradient manipulation. And also we have like the soft modulization, which does some kind of a soft combination of activation using some routing network. And finally, we have the care and Baku, which we described earlier. For all of those baselines, we use SAC as the underlying reinforcement learning algorithm. As we can see from the table, across the training, more consistently outperform all tasks, even from the beginning and even at the like as a asymptotic performance. And as a like a visualization for the performance, this is like the rendered policy on the 10 tasks, which is like this is one of the successful seeds. So this seed achieved 100% success rate.
Sorry, question about this. So those results are like during training, like training and testing environment is the same essentially.
Yes. So for the environment, in maybe I can go into the details of the environment. So the MT meta word has again these two scenarios, MT10 and MT50. Initially, the design for this benchmark, it was intended to have like the multitask setting with a fixed goal position. So you don't change for example, the location of the window or the location of the door and so on. But in this setting that I used, during training and during evaluation, I'm changing the location of the door and the location of the objects in general. So maybe it can be seen from the environments. The location of the windows and also all of the objects is slightly changing between different episodes. That's why we evaluate our approach and all of the other baselines on the same environment, but with different or slightly different positioning of the goal of the objects that we are dealing with. So, for example, the performance after 1 million after 1 million training step, we evaluate all of the policies, and we report the performance for the tasks, for the algorithms, and also for the other time steps. And finally, we report the final performance at 20 million steps, training steps. Was I clear, or I need to repeat?
Yeah, understood. Yeah, got it. So this is like a learning curve, but just in a table, essentially.
Yes.
Okay. Yeah, all right.
To test the scalability of our approach, we tested or evaluated our approach also in MT50, which is like a bunch of 50 different but related, manipulation tasks. But we reported only the final performance. We showed that more also reported the state of the art, also outperformed the recent state of the art, which is Baku, by a huge gap. It's not like a really small gap; it's really a huge gap. And after like evaluating on MetaWord, we found that in terms of sample efficiency, we are good. In terms of asymptotic performance, we are great. And also we can say that more can scale to many tasks. To test like our approach on a totally different environment, where now we are dealing with visual inputs instead of dealing like with the vectors that represent like the angle of the joints and the angular velocities and so on. Now I will deal with pixels. So we benchmarked also our approach on mini-grid, which is a collection of navigation tasks in a grid world settings. We have like three scenarios: MT3, MT5, and MT7, and all of this, like for example, MT3 is a subset of MT5, and MT5 is a subset of MT7. The state, as we said, it's visual, it's an image, and the action space is represented by 7 discrete actions. For the baselines, We also compared against single task performance, but in this environment, we used PPO as the underlying reinforcement learning algorithm. We also reported the performance of the adaptation of PPO to multitask. Also, we tested the performance of our architecture, but without the orthogonality component. So the same exact architecture that I just showed previously in the previous slides, I just removed the Gram-Schmidt process and then reported the results to see the effect of the diversity, because it might be like just a clever design for the architecture. Also, I used the same architecture, the mixture of experts, without the orthogonality, and then I added BC grad on top, so that to solve any task interference problem. From the results, we can see that also more reported really good performance, and also outperformed the single task performance by a huge gap. So now I can say that at least we tested out more on also visual inputs. So it doesn't matter like the type of inputs, doesn't matter like the type of expert that I'm using. I mean, about the technicality, for example, for MetaWord, I used like a dense network to represent the expert. But for example, for here, since I am dealing with images, I used like CNNs. Our optimization problem, our constraint optimization problem had this constraint inside. One solution would be, instead of using Gram-Schmidt and so on, maybe we can just use a soft regularization term. For example, here, optimizing for a Gaussian similarity loss, instead of using totally like hard orthogonalization approach. So here we used a soft orthogonalization of the representation by adding this regularization term to the main objective. Across many grids, we can see also that our approach with Gram-Schmidt is better than the soft regularization. And I think we can agree that the soft regularization, it's hard to tune. It's really hard to tune the temperature of this soft regularization term. And usually it conflicts with the main objective of the problem. However, in our case, we can see from the results that the hard constraining the representation by enforcing such a hard orthogonalization of the representation doesn't really conflict with the main objective, at least in terms of like the optimization point of view.
Right. So I agree with this. However, can you say a word on the compute? Like, is it much more compute intensive to do a Gram-Schmidt decomposition than just doing a soft regularizer like this?
So in terms of the soft regularization, still it needs to compute such you need to compute such a loss every time step. Every time step you fit your algorithm, you need to do such a computation. So it's similar to Gram-Schmidt. However, the drawback of Gram-Schmidt is that you need to compute that during inference. However, for this like soft regularization term, you do that only for during training. That's like one of the drawbacks of using Gram-Schmidt in this position. And that's also like one direction that we could there are also like some options we can do to make this soft mixture of expert setting become like sparse mixture of expert setting. So since we need to every time step we need to orthogonalize all of the representations from all of the experts, then I cannot like it needs a lot of competition to do it compared to a sparse setting where you, for example, like you select 2 experts and then you compute the representations, or maybe you select few experts and then compute the representations. For this like framework, we need to compute all of the representation every time step.
So that takes me to my second question. That's why I was asking. So if I want to put your algorithm on a real robot, right, I need to be operating in real time, right?
Yes.
And the question is, during inference, since you need to compute the Gram-Schmidt decomposition, will that time be okay, in a real robotic setup, or will that be slow and we need to actually do the sparse thing you mentioned before putting it on the real robot?
So I believe like my straight answer is we need to employ such a sparse setting for real robots. We need to have like a sparse mixture of experts to have like a real-time performance. However, the complexity for the Gram-Schmidt is all depends on the number of experts and the dimensionality of your representation. So it depends on the number of experts. For example, for my next ablation study that I did, tests how many like number of experts do I need to achieve good performance. Maybe I can achieve more, but maybe I can be satisfied with just 4 experts, as I just reported. So it depends on the number of experts. For example, we found out that using Gram-Schmidt or in general orthogonalize the representations give you a chance of using less resources in terms of like the number of experts than without doing the orthogonalization. And I think if you used 4 experts, the time complexity will be way less than using, for example, 10 experts without the orthogonalization. So it's an equation, or it depends on like the number of experts and the dimensionality of your representation. And I think the advantage of doing the orthogonality give us like a chance of using less experts, hence less compute time, I think. But for real robots, I am not an expert for real robotics scenario, but I can say that we need this sparse mixture of experts setting to deploy such an algorithm.
Right. Yeah, it makes sense actually. Yeah, I got it. Thanks.
Thanks.
Ahmed, let me ask a quick question.
Yeah.
Am I right that this Steffel manifold will be basically shared by these different tasks
Yes.
that you can see? So it will be, is it possible then pre-compute one good Steffel manifold, maybe with high dimensions, maybe with multiple experts, fine. But like in this case, we will not need to recompute it again and again. And we could use it just one that was computed before.
But we already represent this Steffel manifold with a mixture of experts. So so just to make sure that I understood your question correctly. So you are saying that we can compute the Steffel manifold, which is represented by the experts, right?
Yeah. So I sort of thinking about this representation as what we currently have for the large language models. Yeah, we have these embedding layers that basically embed our tokens to some high dimensional Euclidean space, and then we could actually use that high dimensional Euclidean space as it is basically in order to just apply it for different tasks and for different models. So I was thinking, if this is so computationally, it can be expensive to recompute it again and again, this Stiefel manifold, this orthogonal, this projection on the space of orthogonal matrices. But maybe we could actually do it like a pre-processing step, sort of.
But how can you store such representations? Because I mean, I can return back to the diagram. I'm using the experts to encode such representation. So I need every time step, I need to encode the state to the Steffel manifold. I can agree that after training on certain number of tasks, for example, like I will train on the 50 tasks of MetaWood, and now I will encounter slightly different manipulation tasks. Maybe I can just freeze those experts and then just train the final output layer. I can do that. Actually, this is my next ablation study. So we tried out like, can I use more for transfer learning? Can I?
Yes.
Yeah. Then I. So we tested that out, but on mini grid. So first we learn the mixture of experts, which is like we learned actually like the Steffel manifold, as you said, on the MT3 or MT5, which is like the two scenarios from mini grid, and then we freeze the experts, and then since MT3 is a subset of MT5, and MT5 is a subset of MT7. The novel tasks that which is like the difference between the two sets, we used the frozen experts to train on top of it at the output layer, and we showed the performance in the following plot. So we can see from the plots that the transfer more is way better than the transfer MOE without doing this orthogonalization, which also states that, I mean, doing transfer with good Stiefel manifold can already capture like knowledge about the environments. And if you moved slightly to different environments, but still related, you can trust your mixture of experts to be like good enough to interpolate your new states, your novel states, such that you don't need to retrain again. I totally agree. And I mean, from the ablation study, we found out that this is actually true.
I see. Yeah. Cool.
I can return back quickly to this experiment. So this experiment just like did different runs with different number of experts, comparing our approach with the same architecture but without Gram-Schmidt. And we found out, for example, that Moore with 4 experts is slightly better actually than, for example, 10 experts. And this is like in general waste of resources. So it's better to do the diversity of the experts or doing this Gram-Schmidt such that I use way less experts than if I don't use the orthogonalization of the representation. Finally, we wanted to check if we can interpret the rules of each of the experts. So from our framework, we know that we compute task-specific weights that will combine the representations after the orthogonalization. So those are like you can just save them. You can just, it's like one vector. So these vectors you can just apply BCA on top of it, so that you can see the relations between tasks. From the ablation study, we found out that we can capture some kind of interpretation for the roles of the experts. There is no guarantee, by the way, that we can interpret the role of each of the experts, since we don't enforce any kind of like prior knowledge about the environment or anything. We just let the network design its own experts. But we can, for example, see from the plot that that the pick and place and the big insert side, since they need to like to pick an object and then move it to a position, we can see that they are almost close to each other. For example, the window open and the door open, since they share the open skill, they are also close to each other. Also, like the window close and the drawer close, also close to each other. There are different scales here between the x-axis and y-axis. And also like the button pressed top down and drawer open, I had like some rough time to understand, like to interpret the behavior. But I can see from like the rendering that both of the two behaviors are similar in terms of like moving toward the object and then grasping it, or doing like and then move down and so on. But it's not yet clear. But at least we can say that we can interpret the behavior, since we have already the weights that we computed earlier. We can check if we can interpret the roles of the experts. But in my opinion, the interpretation of the roles of the experts not actually necessary. I don't care if I can interpret the behavior of the experts or not. I care only if I want to do manual transfer learning, for example. If I know, for example, one expert is responsible for the open task, then definitely this is like beneficial for me, so that I can transfer it. And this also can like be part of the extension if we want to make our soft mixture of experts being sparse. This could be like one option. So just to summarize, what we did in this work is to we we wanted to share orthogonal representations between tasks for the sake of like learning diverse experts. We propose a new formulation for the multitask reinforcement learning problem based on like the Stiefel manifold, and we use the Gram-Schmidt to satisfy our constraint optimization problem. And for the meta award, we already provided now the state of the art in MT10 and MT50. And for the future direction, I think applying this concept of a sparsity to the selection of the experts is necessary so that we can lower down the time complexity. And since now we can say that somehow that the representation generated from one expert is different, or at least on average, it's different from the generated from the other experts, then I can freeze some and then add a new one, which should be orthogonal to the previous ones for a continual learning setting. So every time I will add an orthogonal expert without having the problem of like learning similar experts, which is also crucial for continual learning. I mean, that's it for me. If you have any questions,
Thank you.
please let me know.
Thank you so much. Yeah, I mean, this
Thank
was
you. Thank you very much.
fantastic.
Thank
Thank you. Yeah, I mean, good work. I think, yeah, amazing stuff. So I just want to ask one more question for you, actually. So it turns out that deciding on how many experts kind of affects performance and also affects compute, right? Is there a way you think we can determine, the optimal number of experts given some task information?
As far as I know, I don't think so, but I think it's in the literature of large language models. Currently, the focus is to do that actually. Since I haven't worked on large language model like in depth, but I checked a couple of papers recently. I found that they are focusing on like moving from like soft mixture of experts to sparse mixture of experts, and they are trying to use some kind of the task embeddings to select the experts. But regarding the number of experts, I don't have like the knowledge, to be honest. I don't know
Right.
if you have
Okay.
like any information that you can share.
Yeah, so okay, there is an old work, right, from a professor called Hong-Lak Lee. It's a very old work. I mean, very old, but it's an old work. What they were trying to do is they were trying to progressively grow a neural network, essentially, right? So they wanted to, you have a starting neural network, and then they wanted to progressively grow the neural network when it does not have additional capacity to learn some new data that has arrived. So it might be the case that there could be a way to extend that, but into a mixture of experts kind of setup. I need to find the exact paper, but I believe
But
it's called progressive neural nets.
progressive
If I'm
neural
not mistaken.
networks. Yeah, I know it. I know it. This is actually a continual learning paper, right?
It is. It is. Yes, it is. Yeah, but there is one before that. I think this progressive neural nets is not from Honglag. I need to find that. Okay, I need to. I'll find it for you. But
Okay.
they were actually dealing with the sparsity constraints, and they wanted to understand when should I add nodes and layers to the network. And
Yeah.
I'll find that and send it to you. Maybe it could be useful.
Yeah. But also for this progressive neural networks, if I remember correctly, that the good thing about it is that they increase the capacity of sequentially. They increase the capacity of their network, but they activate only the part responsible for the task on hand. So it's different from the concept of mixture of experts, since we actually share all of the experts.
Yeah.
Maybe, in my opinion, doing this the sparse MOE could be the way to go. But again, I cannot answer the question of what is the optimal number of experts based on some prior knowledge.
Yeah.
What I did normally is to as I showed you in this experiment, I did like some runs on, and I found out that on average, after applying this diversity thing, the performance increases with time. Of
Mhm.
course, it will saturate after a while, because every time, in my opinion, every time I'm adding an expert which is like orthogonal to the previous ones, I am extracting relevant to a point where I'm now starting to extract representation with a higher degree, which could be not necessary for solving the task. It could be necessary for example, like having really fine performance,
Right.
it's like high frequency components. So
Mhm.
as I have like orthogonal experts, as I increase those numbers, the experts will not be redundant, but they will capture a relevant but not necessary task representation that can solve the core problem.
I see. Okay.
Um,
And if I got your framework right, the way you update those parameters for those experts is actually based on the reward from the environment, right? Like it's
yes,
the J is the sum of the total discounted reward, right?
yes.
Yeah, this is really interesting because also doesn't this depend on the policy that you use, in fact? Because I mean the
Of course.
quality of your experts, right, will ultimately depend on the policy or not?
Yeah, definitely. Because
Hmm.
here I said that we are using the same framework for the actor and for the critic. So I
Uh,
mean, the actor represents the policy. So I have experts for the policy, and I have experts for the critic, and definitely it depends. I mean, it's like a cycle. It depends on like the quality of the experts. I will generate actions, and depending on those actions, I will update my experts.
Interesting. Yeah, yeah, yeah. Got it. Yeah, fantastic. I mean, amazing work, Ahmed. Really,
Thanks.
really cool.
Thanks.
Chris, do you have any questions? Do you want to discuss?
Yeah, sure. First, thanks, Ahmed, for the really
Yes.
interesting talk, and you have some very impressive work. Um, so my first question is, so I, as I understand, you assume across all these contexts the same action space,
Yes.
and so I'm curious, what would be needed to extend that to? Because you might have different tasks in a real setting, right? Like you have maybe pick and place, and you have sort of non-prehensile manipulation, like pushing or something. And so, in one case, you need a gripper, and the other you don't. So your action space is it's a simple example, but yeah, the action space might be different. So, do you, what might be required to extend your method?
Simply, in multitask reinforcement learning, we have this concept, or we have an architecture choice of having like a single head and multi-head architecture. So in my framework, I have this mixture of experts that encodes the state agnostically without knowing the context. So it doesn't matter the number of actions in the action space. It doesn't matter like the context that I will try to now solve. But the output head is now the essential part. So if I want to have like to deal with different action spaces, I will train different heads,
Mhm.
different output heads. And actually, this is what I did for MetaWord, for example. For MetaWord, I have like the F function, which is like the output module. I have different ones for different tasks. However, the mixture of experts is definitely shared by all of the tasks. So only the F is different across tasks, because I might have the problem, as you said, that my action space is not similar or not
Mm.
shared between all tasks.
Okay. So that okay, great. I have another question about the computation time. So I think Hytham mentioned or asked this about applying it on a real robot, and this grand step is computationally intensive, and I think you mentioned like sparsity. I'm just curious, what is the like for each control loop step? Uh, what is the computation time?
Like in terms of the time, I can give you like the time complexity equation. So the time complexity equation is O of k times d square.
Mhm.
That's the equation. So again, it depends on the dimensionality of the representation generated from each expert and the number of experts. In terms of the time, I haven't for the camera ready. I will do it, but now I don't have it. But as an equation, I think you from the time complexity, you can tell if you are using, for example, four experts and the dimensionality, for example, like 128. Then you have this is like as an overhead on your architecture without doing this Gram-Schmidt.
Okay. Okay. So, I mean, would it be over a second? Would be-
Yeah, sure.
Yeah,
Actually, less than seconds.
less than a second.
Yeah.
Okay, so like maybe yeah. So I mean, generally, if you're doing something like this with position control, maybe 10 to 20 milliseconds is fine for this kind of thing.
I need to double check the exact time,
Mm.
but if I remember correctly, the training time with the Gram-Schmidt increased by around maybe 20%, I think.
Mhm.
But I need to, to report these numbers in the camera ready. So maybe in the camera ready, you can find the exact numbers. I
Yeah,
hope.
great. Thanks. Cool. Yeah, that's everything for me.
Right. Thanks, Chris. So actually, I found the paper I was talking about. It's called
Okay.
Online Incremental Feature Learning with Denoising Autoencoders. So, of course, it might not seem directly relevant. However, the relevant part is when they do what they do in Figure 1 about merging similar features together, right? So they're trying to shrink, right? So I will send it to you on LinkedIn, like the
Okay.
link to the paper. Maybe
Thanks.
it could be something to look into. All right.
Thanks.
So, Ahmed, we have one last question. So we're starting to ask researchers this. So, how has been your review experience at the conferences? And do you have any suggestions to improve this? I know this is on the spot, so you can also say no, but maybe you have some ideas there.
I have the answer because it was ICLR reviewing process was terrible, to be honest. I mean, I had 5 reviewers.
Yeah.
Two of them never replied. So after asking like few questions in the rebuttal, they never replied. One of them said thank you. That's it, without saying if he's gonna like retain the score or doing.
Yeah.
Two of them actually engaged. So I think that the one thing we can do is to force some kind of a deadline for the authors to at least acknowledge reading the rebuttal. This is
Mm.
the minimum thing that we can do. At least, please acknowledge and tell the author that you will retain or you will increase or even decrease your score. But it's really hard to, to do like a fruitful discussion, a fruitful reviewing process, if just me doing the ablation study, doing the work and so on. And for example, like this MT50, this
Mm.
result took me around like 10 days to run, to train,
Mm.
uh, because one of the reviewers asked for it and he never replied. He never acknowledged that I have these results.
Yeah. Yeah. Yeah.
But
Yeah.
that's my straight
No, it
answer.
is frustrating. I understand. I mean, we all had this experience, and I definitely think there's place to improve. So, yeah, I mean, thanks a lot. This
You're
was
welcome.
really enjoyable, and congrats again on your iClear paper.
Thank you.
I hope you the success in the conference as well.
Thank you.
Yeah, thanks again, Ahmed. And with that, I would like to end this second lecture by Ahmed Mehdi. So that's the Mehdi with a fantastic researcher. All
Thank
right.
you.
So I'll see you again in the next episode. Thank you so much.
Yeah.